Hello, in this video we're going to be talking about uncertainty and error. We're going to be talking about how to record experimental uncertainty, different types of error, how they can impact your data, and we'll also be getting into how to depict uncertainty on a graph. So a good amount of this is review. You've learned about a lot of these in your different science courses. In the IB, we're going to start to get a little more serious with how we deal with uncertainty mathematically. So as we get to the end, we'll get into a little bit of that, but for the most part, we're going to review some of the basics in terms of what uncertainty is and how we record it. So one thing to keep in mind is when we say error, some students tend to have some baggage associated with that word maybe. But error is something that is fundamental to science. The idea is everything that we measure has some uncertainty. There is experimental error. You can't know anything perfectly when you do an experiment, when you take data, when you measure anything. It is just impossible to know any value perfectly. That's a fundamental thing. Even if you had the most amazing ruler in the world, you would never be able to measure the length of a piece of paper or whatever. So you really want to keep that in mind. If anybody ever claims that they know anything perfectly, they are lying to you. There is uncertainty in everything, there's error in everything, and that's not a bad thing. All right, so it's not a mistake, it's not wrong when you talk about uncertainty and error in your lab reports. You don't want to be like, this was bad, or I made a mistake, or this was wrong because blah, blah, blah. Error, it's understood that this is part of what we do. Nothing is perfect, and that's part of science. All right, so there are two types of error. Random error is the first one, and this is the most common, the one we're going to deal with the most. This is an uncertainty that comes from just a regular variation of data. If you take the same measurement multiple times, you're not going to get the same exact reading every single time. If you try and time the time it takes a pendulum to swing back and forth with a stopwatch, you're not going to get the same exact thing every single time. And that's normal, right? That's not a mistake. That's how a measurement works. So the fact that you'll get something slightly different when you run different trials, that random error reflects how much that happens. So random error is error that can be bigger or shorter, right? The idea is it moves the value randomly around what we would call the true value. And so this affects precision. It gives us a wider spread of our data, right? There's a statistical spread. We can reduce this by taking multiple measurements, right? The more we take, when we take an average, we expect that if this is really random error and is really randomly sometimes making the reading bigger than it quote should be, sometimes making the reading smaller than it quote should be. If I take a bunch of measurements and average them together, I should get very close to that true or expected value. This is why taking multiple trials in an experiment is really important. In the IB, we typically use 5 as a minimum. In the real world, you want to use way more. The more trials, the better, because you can reduce the effects of this random error. And the other type is systematic error, and systematic error shifts all of your data in one direction. So that's the key difference to keep in mind and to be able to identify them. Random error, it wouldn't prefer to make the data bigger or smaller. It would swing it both ways around the true point. But systematic error will make all of your measurements too big or make all of your measurements too small. The common example is like a calibration error. Like you didn't calibrate your sensor, and it's when nothing's, imagine on the triple beam balance, when nothing's on it, it's not at 0. When nothing's on it, maybe it says it's 1 gram. Then everything is going to be 1 gram heavier than it should be. So it usually comes from some kind of flaw in the design of the experiment or in the procedure, like not zeroing a sensor. So this will affect accuracy. Systematic error is one that we can pretty much eliminate from an experiment if it's a well-designed experiment. If you're talking about systematic error in an experiment, you really need to be able to justify how you know that it's shifting all your data in the same way. So most error that we deal with will be random error, but systematic will come up and you need to be familiar with it. All right, here's the classic picture that I'm sure you've seen in your previous science classes, some version of this when we're talking about accuracy and precision and the difference between those two things. So accuracy is the idea of how close are we to this true value. Target A is like somewhat accurate and somewhat precise, we could say. They're mostly hitting around the point we want to hit, and they're all pretty close together. Target C is really good. It's both accurate and precise. Very accurate, very precise. It's on target, and they're all very close to each other. Whereas target B is very precise. All of these points are basically on top of each other, but it's also not very accurate at all, right? It didn't come anywhere close to the true value. So that's kind of the idea here of accuracy and precision. So A, we could probably say is accurate. If we averaged all these, it looks like it would be a bullseye, but not very precise. They're spread out. So that's the idea of the difference between accuracy and precision. Accuracy being how close you are to the true value, precision being how close together all your measurements are. All right, so let's talk about uncertainty itself and how we measure it. There is an article in the description that we kind of went over in class about why there are so many tides in swimming. This is an interesting application of uncertainty in the real world, and the idea that we don't know these measurements as perfectly as we might want to has all kinds of impacts, like when we're talking about the Olympics and we have to round things and then that affects things. So you can check that out for some context. But the idea is every time you take a measurement, there is an uncertainty. Anytime you ever measure anything, you're going to record it with an uncertainty. And this is how we write those values. All right, so y here is like a generic variable to represent just any measured value that you take. And delta y is how we represent an uncertainty. This is kind of the IB style that you'll see in the data booklet. So this is the value that you measure. This is what you typically think of as the measurement. Delta y is one quantity. This is just the way we represent it, and that means the uncertainty. Just for an example, that would look something like this. You've seen this before, where we could write a measurement of length or something as 17.5 centimeters plus or minus 0.5 centimeters, right? So this is a way of telling me that the measurement I took was 17.5 centimeters. And when I took that measurement, I felt confident that that measurement fell within half a centimeter of this number. In other words, I think this measurement is somewhere between 17 centimeters and 18 centimeters. I'm confident it lies somewhere in that range. That's the idea with how we represent this. Notice you only have to write the units one time. You don't have to write centimeters in both places. That's a little redundant. So this is how we're going to write all measurements that you ever take should be written like this. There is another method of representing uncertainty. In fact, in chemistry, this one's a little more common because you're usually dealing with percentages a lot more. But we can also deal with fractional uncertainty, and we'll talk soon about why this comes up a lot in physics too when we start doing some math. But fractional uncertainty is where we're going to take the absolute uncertainty and divide it by the measured value. And this gives me an idea of how big my uncertainty is relative to the measurement. So if we take that previous example, the fractional uncertainty we would find by dividing the absolute uncertainty by the value itself. So we can see here 0.5 out of 17.5 is about 3%. So we could write this as 17.5 centimeters plus or minus 2.9% or plus or minus 3%. That's also a good way to give a picture of how precise this measurement is, right? So either way is acceptable. The way you want to present all this is with absolute uncertainty, but we will talk soon about where this fractional or percent uncertainty come up. And you'll see those interchangeable. Fractional uncertainty and percent uncertainty mean the same thing. All right, so to review your rules for uncertainty, there's a minimum uncertainty for every measurement that comes from the device. This is called the device uncertainty. We'll talk as we get further in the course about times where you're going to want to bump up this device uncertainty, but this is a minimum. Your uncertainty for a measurement is going to at least be equal to the uncertainty from the device that you use. So you want to remember that if you have an analog device, the uncertainty is half the smallest increment. The idea here is that we can read in between the lines. So an analog device is any device that has a scale like this that you read with your eye. Something like a ruler that has hash marks. So the ruler is a classic example, but it's marked every tenth of a centimeter or every millimeter. And the idea is if I'm trying to measure something, I have a stick and it like comes out to here. I might guess that it's 8.1 or 8.0, but I can also eyeball in between, and I can even guess that the stick is 8.03 centimeters long. And I can get away with that because I'm going to apply an uncertainty of 0.05 centimeters. So what I'm saying is I'm confident within half of a tenth of a centimeter, if you want to think of it that way, or I'm confident within 0.05 centimeters. So I could say 8.03, thinking that it's for sure somewhere between 8.08 and 7.98, right? So that's the rule for analog devices, because you can eyeball in between, and you need to eyeball in between and make an estimation. That's the other part of analog devices. If you just write 8.0 or 8.1, you're not being specific enough with an analog device. You have to estimate to that, in this case, second decimal place. But you have to estimate to that extra place because you can eyeball in between. Digital devices are different because you can't do that. You can't look at it by eye and decide, that this last digit is like closer to the 9 or closer to the 7. We really don't know. So we just have to use the smallest increment. So the stopwatch is a classic example. This is the 10th second. So my uncertainty is a tenth of a second. Right, it's just one digit in the smallest increment. Over here on a multimeter, whatever the heck this is measuring, it looks like volts. If we have 0.385 volts, the uncertainty would be 0.001 volts, right? One digit in the last increment. This thing can go up. We assume it could give me a reading at 0.386. It can give me a reading 0.384. So the increment would be 0.001. So that is the uncertainty. So those are the two rules. You have to memorize them. You're going to use them all the time. So they're very important. Make sure you know them. All right. One other thing we can talk about is how we represent this uncertainty on a graph. You know how to represent it on data tables, by using the absolute uncertainties, but we will also use error bars to represent uncertainty on a graph. And you can see here in the picture the general idea, but error bars will show us visually that uncertainty. It shows us this idea of like plus or minus. In this course, we're going to use Logger Pro for all of our graph work. Logger Pro is amazing, especially for IB. There are parts of Logger Pro that have literally been designed with the IB curriculum and the way the IB wants you to do stuff. So Logger Pro is what we're going to use for all our graph work. You're going to do your data processing and all that in Excel, most likely, and then we're going to bring that over to Logger Pro to make the graphs, because it is very, very, very good for the style of graph that we want. Okay, so since we know that experimental values have uncertainty, and what we'll get to soon is that calculated values also have uncertainty, slope should be no different. And in physics, slope and slope analysis are very, very, very important. So finding the uncertainty of a slope is something we would really like to do, and error bars help us do that. So what we're going to do, first we put these error bars on, and we will go over in class together how to mechanically do that in Logger Pro. But the idea here is these error bars just show my uncertainty, right? I can see these vertical error bars go up and down. So this first value would be 3 plus or minus 1. It's 3. It can be as high as 4. It can be as low as 2, right? So these error bars show me the spread of that data. So I can literally plug in my absolute uncertainties, and they visually get represented on the graph here. The idea is I can put all kinds of lines on here, though. Logger Pro will put the best fit line on there for me, but I could probably put something steeper that still crosses my error bars. I could put something less steep that still crosses my error bars. So I need to consider all of those. I need to consider the range, and I'm going to create two lines. I'm going to create lines of minimum and maximum slope. So I'm going to create the steepest line I possibly can and see what that slope is. I'm going to create the least steep line I can and see what that slope is, and those two I'm going to compare, and that will help me find the uncertainty. I'm going to look at how to do that. right? So we need to, this takes some messing around. It's not a perfect rule for how to do this. You really have to do it by eye, and Logger Pro makes it really easy to do this with one of their features. But we need to show the maximum minimum possible slopes that consider all the data points. So they should, in an ideal world, cross through all of the error bars. They should at least come close to crossing through all of the error bars as best you can. And so the error bars we can think of as creating a box, and we'll look at what that looks like on the next slide. But we want to imagine that we're trying to pass these lines through these boxes. Here's the formula that we're going to use for the uncertainty of the slope. And we'll talk a little bit more about why this works, but we can think of it as just half the possible range. I take the largest slope I have, subtract the smallest slope I have, and divide them by 2. So that's the formula you're going to use all the time for finding the uncertainty of a slope. All right, so here's that same graph, and when we're talking about the boxes, this is what we mean. So we can imagine with the vertical and horizontal error bars, I have this range. When we take data in an experiment, this is something you want to try and think about and start wrapping your head around, because it's very opposite of what you typically think, maybe especially in terms of science. But like we said in the beginning, we don't know anything perfectly. We don't know any value perfectly. And so just because I measured this value to be 3, there's an uncertainty. It could be somewhere between 4 and somewhere as low as 2. There's nothing special about the 3, really. So when you take a data point at all in life, when you're measuring something, you don't know it perfectly. You'd never know an exact value. We really know like a fuzzy region. So the best we can say is that this measurement falls somewhere in here. All right, and this whole box is your piece of data. This whole box is just as valid as this point. It's more valid than just this point. This point by itself is meaningless because it has no uncertainty. So you need the error bars, and this tells me the region where that measurement is. All right, so this first region here is what I need to consider, and this is what we mean by a box. And we can put that on all of them. You're not going to literally draw these on your graph, but this is just to help visualize. You want to kind of visualize these as you're doing it. A lot of experiments too, you're going to have very, very small horizontal error bars, or maybe even you'll have big horizontal bars and small vertical bars. That's less common. But either way, you can think of it more as just a line if it's not a box. So if it's just like a vertical bar and the and the horizontal bars are very small, that's okay. We just think of it as a line up and down, and then it just has a cross through the line. So imagine like a rectangle that's just like really, really, really ridiculously skinny. All right, so to draw these minimum maximum lines, this is what it would look like. This blue line represents, to me, the steepest line that I could draw that still crosses through all of these boxes, right? I am including this data point, this data point, this data point, this data point, and this data point. And that's valid because this data could be anywhere in this box. Then the purple line is the opposite. This is the least steep line that goes through all of the error bars, and I couldn't make it any, shallower. So this demonstrates visually the range of the slopes that I should or could have in my experiment. And so I'm going to use these then to talk about an uncertainty, right? You can imagine if these error bars were way bigger and the blue line was like this and the purple line was like this, I would have a much more uncertain slope. I wouldn't know it very well. Whereas if the error bars were smaller and these lines were closer together, I would know my slope really well. But here we can see the slope is somewhat spread out. There's different slopes that are possible. And so I need to find that uncertainty. All right. Here's a different data set, but this is from the experiment that we are doing in class where we're trying to find G, right? We have weight versus mass, and I have 3 different lines on my graph here that show me minimum and maximum and average or best fit slope. And so I'm going to use these to find the uncertainty. So I just need to do the maximum slope, subtract the minimum slope, divide by 2. So in this case, my maximum slope is 10.3-ish. My minimum slope is 8.6-ish. So I'm going to subtract those and divide by 2. And I get 0.85 or 0.9. One rule that we'll go over in more detail soon is that all of your uncertainty in an experiment gets rounded to 1 sig fig. So we're going to round this to 0.9, and then that would make my actual slope with its uncertainty 9.5, which comes from this. Your slope always comes from the best fit line that Logger Pro gives you because it's done the work for you. It's taken all 5 data points, told you the average best guess at the slope. Because my uncertainty is 0.9, I'm going to round this to the 10th place. That's another rule we'll kind of hammer out in the future. But that's how we're going to do all these uncertainties. And so all that put together, my slope ends up being 9.5 plus or minus 0.9 meters per second squared. Since I know the slope of this line is g, I have experimentally found the acceleration due to gravity to be 9.5 plus or minus 0.9 meters per second squared. So if you looked at the slope of 9.5 and said you're wrong, I would say, with uncertainty, this is totally validates the laws of physics, right? I have not broken physics. Physics works in the lab room as it does everywhere, and for sure, somewhere in here is the true quote value for the acceleration due to gravity. And in an experiment, this is the best I can do. We will think throughout the year of what kind of things could we do with the experiment to make this value better. Obviously, it would be better to get a smaller uncertainty to have a more precise answer. But there we go. That's the uncertainty based on the way we did this experiment, the data we have, and that fully and accurately reflects what I found and how well I know what I found, which is very, very, very important, especially as you go through the IB. All right, so that's the idea, the basics ideas of uncertainty, how we kind of measure and present them both in numbers and on graphs, and how we find the uncertainty of a slope. We're going to do that so many times this year. It's going to be a blast. So there you go. Have fun.